Hello everyone, welcome to Rasaayana Institute of Sciences. So we are offering an intensive coaching for IIT Mains Advanced as well as Neet. Okay, so myself Dr. Rajesh Kumar Pogaku, your concerned chemistry faculty. In this particular video, we are going to discuss a most important concept in organic chemistry, that is concept of enantiomers. Okay, so enantiomers. So try to pay some attention while listening this concept, because it is one of the most important concept, is almost all linked with more than two topics. Okay, so based on the enantiomers, one can easily identify whether given molecule is optically active, chiral, achiral, otherwise whether it is optically active or not. Everything will be cleared if you know the concept of enantiomers. Okay, so what actually enantiomers are? So enantiomers are generally non-superimposable mirror image isomers. Enantiomers are non-superimposable mirror image isomers. Don't think that enantiomers are mirror image isomers. All mirror images are not enantiomers. It should be non-superimposable mirror image isomers. Right? Next, enantiomers are, if I say the word enantiomers, that enantiomers are always optically active. So what actually optically active means? Any stereoisomer, if they rotate plane polarized light, that isomer is said to be optically active. Okay, now one more term is there. Enantiomers are optically active. It is the same way enantiomers are chiral. Chiral, optically active, both are same. So try to focus on chiral as well as chiral center. Chiral center, chirality not same. Chiral center, chiral is not same. So I can say that enantiomers are optically active compounds which are chiral in nature, and they have a non-superimposable mirror image isomers. Means we will get a mirror image. That mirror image, if you expose on original molecule, they should not be same. That is called non-superimposable mirror image character. Okay. So if I take two enantiomers, generally enantiomers are represented by E1, E2. Two enantiomers having generally identical physical and chemical properties. Identical physical and chemical properties. Almost all same physical properties you can expect for two enantiomers, such as melting point, boiling point, solubility, density. Everything between two enantiomers are remain same. Okay, it is same way chemical properties. So both enantiomers have a same characteristic property while reacting with a selective stereoisomer. So that's why physical property of enantiomer as well as chemical property of enantiomers are almost all same. It is same way, if I concentrate on enantiomer, especially in selective character where it can be distinguished very easily, that is rate of reaction. Okay, two enantiomers having a differ in their rate of reaction. Rate of reaction is differ. It is completely different in rate of reaction. Two enantiomers having different rate of reaction. It is same way two enantiomers having different biochemical reactions. Biochemical reactions. Two enantiomers having different biochemical reactions. Two enantiomers having different rate of reaction. Okay. So if I take plus glucose is a enantiomer. It is same way minus glucose. These two are enantiomers of one molecule, that is glucose. Plus glucose, minus glucose. If you concentrate plus glucose is generally used for animal metabolism. It is used for animal metabolism. It is same way fermentation process. But if you concentrate on minus glucose never help in animal metabolism and fermentation process. Okay, so if you intermix two enantiomers, if I am intermixing these two enantiomers, that is responsible to give racemic mixture. Racemic mixture is a compound which is intermixing two enantiomers, responsible to give a sample. That sample is nothing but a racemic mixture. So intermixing of two enantiomers of a molecule always responsible to give racemic mixture. Okay. Suppose if you take two enantiomers, E1, E2, Suppose plus minus if I write, that is nothing but a racemic mixture. If I write only plus 1, only minus 1, that is nothing but E1 and E2. Okay. So, two enantiomers generally are isometric in nature. Isometric. Isometric nothing but they having same energy. Okay. So, they can rotate plane polarized light. Two enantiomers can rotate plane polarized light, but one enantiomer rotate clockwise, other enantiomer rotate anti-clockwise, quite opposite in direction. All enantiomers are optically active. Every enantiomer is isometric in nature, and two enantiomers of one molecule having same energy. Same energy nothing but isometric species. Okay. So, when enantiomer is going to react with a new enantiomer, see, every molecule will give two enantiomers based on some selective character. If the two enantiomers, one of the enantiomer, if they combine with a new enantiomer, this is the enantiomer of a new molecule. So this is responsible to give diastereomer. This is not an enantiomer of one family. It is enantiomer of a new molecule. So enantiomer of new molecule combined with enantiomer of reference molecule always give a diastereomer. Suppose see E1, E2. And see, I am combining with this E3, then see, this will give one more diastereomer. Okay. So, two enantiomers, when they combine with a Chiral reference, this is called Chiral reference. When they combine with Chiral reference, always develops a diastereomers. Okay. Diastereomers may be optically active, may be inactive. Don't think that enantiomers are optically active, diastereomers are optically inactive. That may be depends upon the proper connectivity within the molecule. Okay, next. Suppose if I take any enantiomers, enantiomers are completely free from symmetry elements. Completely free from symmetry elements. Okay, means they don't have plane of symmetry, they don't have center of symmetry, they don't have rotation and reflection axis. So, try to remember, each and every enantiomer doesn't have any kind of symmetry elements. They don't have any kind of symmetry elements. Okay. And any molecule or any single isomer having single enantiomer. Suppose one molecule shows an enantiomer to second molecule. Okay. That molecule never show enantiomer to other molecule. Suppose if you are standing in front of a mirror, your mirror image is always your enantiomeric character. That doesn't show any enantiomer to other molecule. Right? So, I will give one example. In order to show enantiomerism, molecule required Chiral center. They required a Chiral center. They required a Chiral axis. Anyone is required. Chiral axis. They may carry Chiral plane. Chiral plane, otherwise they carry Chiral helix. So in this one, the common word is Chiral. If any molecule having a Chiral, then that molecule is said to be optically active. Suppose if it is optically active, may not be enantiomer. It may be a diastereomer, it may be a enantiomer. So it is always depends upon their partner. Based on the partner, your character is going to be changes. Suppose I will give an example. There you will find the enantiomer clearly. See, this is a molecule known as lactic acid. So this is a center where 4 different substitutions are present. That is called Chiral center. Right? Now, if I write its mirror image of this one. See, this is OH and this is H. Now I can say these two are enantiomers. So I can simply represent a mirror image over here now. Mirror image of these two is nothing but enantiomers. One Chiral center you can believe. One Chiral center mirror image is always enantiomer. What is Chiral center? The center of a molecule having 4 different substitutions are nothing but Chiral center. This center having carboxylic acid, OH, H and CH3, and it is quite exact mirror image. So I can say these two are enantiomeric in nature. Okay. So this is lactic acid, and here one more. Same molecule, almost all looks same. See, this is called mandelic acid. How to identify one more way of representing enantiomer? Suppose rotate this model by about 90 degree. Okay, this is called Fisher model. If I rotate by about 90 degree, like this, complete rigid rotation. So carboxylic acid will come right side, then OH will come over here, pH and here hydrogen. Now, if you rotate any Fischer projection, if molecule having one chiral center by about 90 degree, this is also belongs to enantiomeric in nature. Okay, and very very important thing is, suppose if any molecule having more than one chiral center, see this is a molecule having more than one chiral center. Now, so generally if you see clearly, sometimes they won't give mirror image, but right now see what I am giving is, it is a molecule having two chiral centers. One chiral center mirror image is always enantiomer, that is not a problem at all. If molecule having more than one chiral center, mirror images may or may not be enantiomeric. So I am taking one example. See, carboxylic acid, and this is OH, and here it is OH, H, and this is H. If you observe this clearly, this molecule mirror image is this one. So don't say blindly mirror image is enantiomer. Suppose take this molecule and expose on this one. And what happens, see, here right side OH is there, here left side OH is there. So it is a non-superimposable. So it is a mirror image and we are getting a non-superimposable, but still this is not a enantiomer. Okay, this is not a enantiomeric here, because this molecule having a plane of symmetry. Within the molecule symmetry is present. So this is called mesotartaric acid. If any molecule having plane of symmetry within the molecule, if molecule having plane of symmetry within the body, that molecule is said to be meso. If I say the word meso, that molecule is always optically inactive. Optically inactive nothing but it is not a enantiomer. Remember, every enantiomer is optically active. I am saying it is not a enantiomer. If it is not enantiomer and if it is having any symmetries within the molecule, that molecule is said to be optically inactive. Right? So blindly remember one point. For showing enantiomeric character, don't think that mirror image is enantiomer. So this is a mirror image. Take this model and try to place on this molecule. Then what happens? Here H and this is OH. So both are not same. They are non-superimposable. Non-superimposable, and it is a mirror image of this one. But this statement is not applicable every time. Okay, so it is a mirror image, and if you place on this one, it is also non-superimposable. But this is not a enantiomeric at all, because see, I will show one technique how to identify enantiomers. But right now remember, one chiral center mirror image is always enantiomer. That point you remember. Here one chiral center, here also one chiral center. This molecule having two chiral center. Two chiral center mirror image may or may not be enantiomeric in nature. Right? I will give one more. See this. So almost all similar concept, but what happens, see, this is called active tartaric acid. Now I am giving a active tartaric acid. This is H, this is OH, and here OH, and here H. Now see this model, it is a mirror image, and this molecule having no plane of symmetry. This is enantiomeric in nature. This is enantiomers. So last case is mesotartaric acid. That is optically inactive. It is not an enantiomer, but right now it is a enantiomeric in nature. Okay. Now I will give one more. This is carboxylic acid, CH3, and here it is OH, and here OH, H, and here H. Suppose if this model mirror image if I take, okay, so this model mirror image is become enantiomeric. Now see, this is enantiomeric in nature. Why it is enantiomers? Only simple reason. Simple reason is, if I want to suspend any plane of symmetry, or if I want to suspend any center of symmetry, all are completely absent here. See, this substitution both are not same. Suppose this substitution if it is same, and if these two are orienting on same side, that image is almost all same. If it is same, on that time it is not an enantiomer. Okay, and one more. See, in this molecule, this is CH3, and here bromine, and here chlorine, hydrogen. Chlorine, hydrogen. So then I am writing its mirror image. Here bromine, chlorine, hydrogen, hydrogen. So Is it mirror image or not? Yes, it is a mirror image. No plane of symmetry. I can say these isomers are belongs to enantiomeric in nature. They are belongs to enantiomeric in nature. Okay. So suppose if I take any wedge model, this is a wedge model. Thick line indicates above the plane and dotted line indicates below the plane. This is OH and here it is hydrogen. Now, so in this wedge model there is a presence of thick line as well as dotted line, which indicates above and below the plane. When you suspend a plane in front of this isomer, you will get this one. Now they carry one chiral center. One chiral center mirror image is always enantiomeric in nature. Okay, so always above is above itself, below is below. They never change their orientation because mirror image always above is above, below is below. Okay, so like that variable models we can identify whether they are enantiomeric or not. So right now I will show one technique how to identify enantiomers with a proper technique. Okay, now see, I am going to take a mesotartaric acid. This is called mesotartaric acid. One of the best technique to identify enantiomers clearly. Now write down its image. I am writing its image. Try to listen carefully and you will enjoy this concept and you will understand clearly and you can apply very easily. So you can identify any enantiomeric pair irrespective of their direction of rotation. So generally you people will think that enantiomer is nothing but mirror image. Mirror image is not enantiomers every time. You need to have some proper orientation with respect to molecule and they having a proper connectivity and they should have a proper symmetry elements. Okay, based on that particular concepts we can say whether they are enantiomers or not. So first thing, symmetry. Plane of symmetry is there, mirror image is optically inactive. Right. So first you take two stereoisomers, whatever they given, try to take the image, rotate image by about 180 degree, in plane 180. You need to rotate like this. This is image of this molecule. Then what happens? Carboxylic acid above, other carboxylic acid is below. You can get like this. Now if I rotate 180 degree like this, these two OH groups will orient towards right side. Right? Now remember, this is the isomer produced by this one by about 180 degree in plane rotation. So these two isomers are identical. If you rotate any model by about 180, that becomes identical. Identical isomers are called homomers. Now the concept is, this image I rotated by about 180, I got this one. Now take this and place on original molecule. I am taking this model and I am placing on this molecule. Then what happens? This molecule both are same. Then on that time, these two are not enantiomers. Rotate image by about 180 and try to take that molecule and place on original molecule. If both are same, they are not enantiomers. So one more example I will give. Same. Almost look same, but see the difference. This technique will most helpful for variable competitive examinations, especially Iit as well as Neet. So you may expect a gunshot question from this. Observe clearly. It is a mirror image of this molecule. Then how to check enantiomers? Rotate this model about 180. Now I am rotating by about 180 degree. Rotate this. If I rotate, try to rotate clearly and try to write the proper orientation of the groups or atoms around the center. See, if I rotate here, this chiral center goes here. Now, if I rotate here, this goes left side. And if I rotate like this, this goes this side. And here hydrogen, and here it is hydrogen. Is it right? See, if I rotate this model, this goes left side, this goes right side. This comes here, this goes this side. Now, take this isomer. See, this molecule I rotated by about 180, so this is a homomer of this one. These two are identical. Now, this is a rotated isomer. Take this and try to place on original molecule. See, here H is there, here OH is there. They are not same. If they are not same, blindly remember they are belongs to enantiomers. Okay, so that is a technique to identify enantiomers in a given molecule. Okay, just make a short revision. See, non-superimposable mirror image isomers are enantiomers, and don't think mirror image is always a enantiomer. So all enantiomers are optically active. This point is helpful for your examination. Every enantiomer is a chiral. Every chiral is optically active. Two enantiomers represented by E1, E2, they are having identical physical and chemical properties, differ in their rate and biochemical reactions. So they will rotate plane polarized light equally but opposite in direction. They are isometric. Remember, isometric nothing but having same energy. Two enantiomers having same energy. That is the meaning of isometric. When any enantiomer reacts with a chiral reference, they will develop diastereomers. We know diastereomers having a different chemical and physical properties. Next, C. Enantiomers are free from symmetry elements. Any single isomer having single enantiomer only. So they require some selective properties. If these properties are present, mostly they are enantiomers, not always. One chiral center mirror image enantiomer. One chiral center 90-degree rotation. See, this is one chiral center. If I rotate 90 degree, that becomes enantiomer. So don't expect every time mirror image every time. Sometimes they will rotate and they will give. Now, if any molecule having plane of symmetry, mirror image is not an enantiomer. It is having a plane of symmetry, mirror image is not enantiomer. This is called lactic acid, mandelic acid, mesotartaric acid. Okay, so few examples I given just now. It is enantiomeric because no plane of symmetry. It is also enantiomeric, no plane of symmetry. And it is also enantiomeric because there is no symmetry elements. So these two chiral centers are not same. Then mirror image is enantiomer. Now this chiral center almost all looks like mirror images. Completely above the plane, below the plane, below the plane. Now this is also enantiomeric in nature. And finally, a shortcut to identify this concept. Take a molecule, write down its image. It's most important one. After writing the image, rotate image by about 180. In plane 180. This is called in plane 180. So like this we need to rotate. Then you will get this one. Take this molecule and place on original molecule as it is. If both are same, that is not an enantiomer. So I am taking this molecule image. This image I rotated by about 180. I got this isomer. This isomer if I place on original molecule, both are not same. If both are not same, then these two are said to be enantiomeric in nature. Clear? So that is about concept of enantiomers. Now we will see some questions. How there is a possibility of asking questions, just see now. Just read that question. Which of the following is chiral molecule? Every chiral molecule is optically active. Okay? If I say the molecule is chiral, if they carry one chiral center, it is optically active. See, there is no one chiral center. Here there is no one chiral center. Here one chiral center is there. See, carbon having hydrogen, acid, chlorine and hydrogen. One chiral center. It is chiral. See, this carbon having three identical groups. It is not a chiral molecule. Chiral center, if one chiral center is there, if molecule having only one chiral center, that molecule is said to be chiral molecule. Because one chiral center is always optically active, always enantiomeric. Next, among the following optically active compound is, see, these molecules are not easy to understand right now, but I can say that this molecule having one chiral center, optically active, this is called chiral axis molecule. This you will understand clearly in chiral axis properties, but right now remember, along this axis if you see, if this carbon having two different substitutions, then that molecule is said to be chiral. Yes, this and this having different substitutions. It is chiral. And this carbon, two different substitutions are there. This carbon, two different substitutions are there. Biphenyls. So it is also a optically active. So these two are chiral axis molecules. These two are chiral axis molecules, and this is said to be chiral center molecule. Right? So especially for showing optical activity, one point just now I revealed. They should carry chiral center, chiral axis, helical axis, chiral plane, etc. Right now there is a presence of chiral axis. This is chiral axis, here chiral axis. So here one point is there. That point is called Chiral center. Around center, if any new arrangement is observed, that is called Chiral center. Along axis, if new arrangement is observed, that is called chiral axis. So now these all isomers are optically active. Simply focus on this point. If this carbon having two different substitutions, maybe they may be repeated. They are said to be disymmetric molecule. They are asymmetric in nature. Asymmetric is nothing but optically active. Okay, and here also same. If you focus on these two carbon, two different, here also two different, it is also optically active. Next. Now go through this. Which of the following are enantiomeric pairs? See, is it a mirror image or not? Yes, it is mirror image, it is enantiomeric pair. Now see this. Plane of symmetry present. Mirror image is not enantiomeric. But here see, it is also two bromines are towards right side, but here right side, left side, it is diastereomer. Answer is not all. Only one pair is mirror image. So answer is A. One chiral center, mirror image is always enantiomeric. You try to focus on that point. Next. See, the enantiomer of molecule A is to this molecule which is enantiomeric in nature. See this two bromine chlorine opposite, but here bromine chlorine same side, this is not exist. Here see, if you write mirror image of this one, now this molecule if you rotate like this, you will get this one. If you rotate in plane rotation of this molecule, you will get this one. So now it is a homomer of this one. So these two are same. Now take a image of this molecule. Take a image of this molecule. I am writing mirror image. You need to check like this. Here bromine, hydrogen, and this is chlorine. Rotate by about 180. This shortcut just now I given. This is CH3. If I rotate here, now this chlorine, if I rotate, you will get here, and this bromine over here. Hydrogen, and here one more hydrogen. Okay, see this molecule and this molecule. Now this molecule image is this one. If you rotate 180, it becomes homomer. These two are homomer. Take this molecule and this molecule. This becomes enantiomer. So answer is C. So it is impossible because chlorine, bromine both are same side. Right? This is one of the most important concept to identify the optically active isomer, enantiomers and chiral isomers. Next. See, the number of optically active compounds among the following. This is also most important question. Three areas will be covered in this class. What are enantiomers? What is optically active isomers? What are chiral isomers? Optically active nothing but all enantiomers are optically active, all chiral molecules are optically active. Just now one point I given. See, one chiral center always optically active. So this is optically active. See, carboxylic acid, bromine, chlorine, phenyl, one chiral center, it is also optically active. This molecule having plane of symmetry, it is not optically active. Every meso is optically inactive. Meso. If any molecule, if you suspend a plane or axis, above part equal to below part, that is optically inactive. Now, if I suspend a plane here in this molecule, bromine same, methyl same, it is a meso. It is also optically inactive. Next, if I suspend a plane here, chlorine same, but phenyl and methyl not same. Okay, so I can say it is optically active. Remember, maybe chlorine same, but here phenyl and methyl both are present. So they are not same. I can say they are chiral isomers. But bromine, now this molecule is meso. If you suspend a plane above part equal to below part, that is meso. And if you suspend a plane above part equal to below, that is meso. So now these two are meso, optically inactive. One chiral center active, and here one chiral center, more than one chiral center is there. So meso half of the mirror image, it is not meso because phenyl and methyl are not same. So I can say this is optically active. So the number of optically active isomers are 1, 2 and that is 3. So your answer is 3. So like that, some selective questions you can expect from concept of enantiomers. It is a most important concept where you will identify framing of questions related to enantiomers, diastereomers, optical active isomers, at the same way chiral isomers. Okay, so that is about this concept. Hope you people understand this concept. Okay, so such type of videos we are going to upload every day. Try to follow that videos and try to see the classes in free of cost. Okay, thank you for listening and keep supporting us. We are keep on uploading these videos every day. Thank you.